Alright, ladies and gentlemen, recording has started. So, as I just stated for you guys, but did not state for the recording, today's class starts with a couple of videos. Those videos are both pretty short. We'll watch the two videos to start class. They relate to topics that we are going to talk about today in class. Some of them are funny, some of them are just kind of make you shake your head a little bit, right? But, like I said, they both relate to what we're going to do. So, to start off, we are going to start here. And I think there is a ad that we need to watch. Oh, hold on a second.
Oh my gosh, I thought that was you.
So we've kind of had a debate.
To clarify, the person in the video is wearing blue, and so is Mr. Planasek. Just so. And then Vinny's almost
Some people thought that this person looked a little bit more like Mr. Tom's than me.
Yeah, he looks
This guy looks shorter though.
So you can tell from that waist shot how tall he looks.
I was gonna say. Next to the trees.
He's got a really long midsection, Becca. That's you can't see it. You know,
I guess.
All right, so now that we have some sound, we can watch this whole video. So, without further delay, here we go.
Hi, I'm Chris Davis from Buck.com. As the days get longer and the temperatures get hotter, it's always fun to find activities to do with the kids that are easy to prepare, fun to do, and have the potential of being refreshing. A water balloon toss is always a crowd pleaser. To get started, you'll need a package of water balloons, a small nozzle, and of course water. You can use regular party balloons, but be aware of who you're playing. Party balloons are much larger, they hold more water, and they can get pretty heavy. Tweens and teens tend to like this option, but it usually doesn't work very well with the younger kids. Once you've filled your balloons, pair off your players and have them stand a few feet apart from one another. Each pair stands face to face with one holding a water balloon. The first toss is made, after which each player takes one step back. Continue alternating tosses between players. Each time the balloon is tossed, take one step back. The pair that has their water balloon intact the longest wins. A couple of tips. Playing over grass as opposed to pavement or concrete may give your players a few second chances. If a player drops a balloon on a toss, it may bounce and roll on the softer grass surface, whereas it will most certainly break over pavement. Also, providing a little give when you receive a toss may allow your balloon to survive just a little bit longer. You can add a few variations to this. If you only have enough players to form one team, have them concentrate on the maximum distance that they can throw the balloon without breaking it. Or if you're playing with younger players who don't want to catch the balloon, provide them with a target to aim for. No matter how you run your water balloon toss, it's all about having fun, and it usually turns into a water balloon fight before the day's through. To learn more, check us out on the web at about.com. Thanks for watching.
They threw 4 balloons at him and only like one of them burned. Alright, so that was the first video. Second video we are going to watch is here. And it's from Cincinnati.com.
Today is a big day. Today, we're
Cleveland Clinic does have a children's hospital as well. Alright, so this one is from Fountain Square in Cincinnati, and details the adventures of the Freaky Friday water balloon toss. Alright, so here we go.
The winners of each heat will then have a toss-off for the overall win, and the overall winning team will receive another 2 rounds of golf, super soakers, and the coveted first place medal. 3, 2, 1, go! Yeah, Alex! So the drops are safe. Even if you're in the rewind set, that's where you're at. Oh, and I don't mind. I once you said in here.
When they move back, we have to move.
All right, you ready? Ready?
The two videos that we discussed lead us into the topic of momentum and impulse. So, we've learned about Newton's second law in this unit, that dealing with acceleration and then the things that affect acceleration like net force and mass. But when we look at what acceleration does, there are a couple other factors that we have to take into account. So we start with this idea of momentum. Momentum is a concept that when Newton actually was putting together these laws, he thought about things in terms of momentum as opposed to acceleration. So this is kind of more Newton's second law in its real form. Some people look at it as the measure of an object's motion, but what does that actually mean? I don't know. Like, what are we measuring about the object's motion? And then I've also seen it described as inertia in motion, which kind of seems redundant because inertia is supposed to deal with things that are moving as well as sitting still. So, instead of looking at trying to explain momentum, let's just define momentum. The instantaneous momentum of an object depends on its mass and its current velocity, or its instantaneous velocity. Instantaneous is a word that we ran into last unit, right? And that means at this moment. What is it doing right now? We calculate the momentum of an object by taking that mass and multiplying it by the velocity. So m times v. We use the p to represent momentum because from what I understand, when Newton was kind of going through the process of developing these ideas, he referred to it first as quote-unquote progress as opposed to momentum. So P represents momentum. P is equal to m times v. Momentum is a vector quantity, which means it has magnitude and direction. Oh yeah. So we have to take those into account when we're looking at analyzing the momentum of an object. The magnitude meaning how much momentum does it actually have. So that's going to depend on its mass and then its velocity. But it also takes into account which direction we're going. An object going one direction has a different momentum as an object going the opposite direction, because if you're going to change their motions, you're going to have to do something different to them. So the direction is important. All right, good with momentum so far. Okay. For the next part, let's get out of here and let's go here. So, does that look familiar? Hopefully.
Yep.
Yeah, that's Newton's second law, relating force and mass and acceleration. And we learned that force and acceleration are directly related and mass and acceleration are inversely related, and all that's true. But there's something that this equation doesn't quite take into account. But we can make it part of this equation by going back to something we did in the last chapter. In the last chapter, we introduced acceleration. In order to calculate the acceleration of an object, what do you need to know? The time and the initial velocity, but also the final velocity, because we got to know the change in velocity, right? Acceleration is the change in velocity divided by the time that it takes. So, if we take this equation, keep this the same, keep this the same, but now we can substitute in, not bad. We can substitute in this expression for acceleration. Does that make sense? Why I just did that? That's how we calculate acceleration. So, now let's do a little math. I'm going to multiply this side of the equation by t. That's going to cancel these two t's out. But if I multiply one side of the equation by t, I got to multiply the other side of the equation by t. And so we end up with this equation. Anyone see where I got that equation from? That is Newton's second law, just rearranged and defined a little bit differently than we defined it before. There's one real obvious difference, something that shows up in this equation that we haven't really considered before. And what is that thing? The time part of it. If I have this stack of books up here on the table, and I hit them really, really hard, but I only hit them very, very hard for a very short time, are the books going to move all that much? Even if I hit them really hard, but I only hit them for a very short time, how far are they going to go?
Not that far.
Maybe not that far, right? Obviously, it depends on how long I hit them for, right? But I could then push on them with a much lower force, but if I keep pushing on them for a longer time, is it possible I actually could move them more with the lower force than I did with the bigger force? Yeah. So if we're really going to look at how much does the motion of this object change, its change in velocity, we have to consider both the force that we apply, but also the time over which we apply that force. And we refer to this equation as the impulse momentum equation. The impulse momentum equation looks like this. We just wrote it down, right? Don't get confused with the t and the delta t. It's the same thing. Right? How much force do we apply? How much time goes by? So the impulse momentum equation relates together how much force, how long do we apply that force, and then what is the ultimate change in the motion that occurs because of that force? So how much force do we apply? How long do we apply that force? And then what's the ultimate change in the motion that occurs because of that force? Or the change in the velocity? So this equation tells us that the change in momentum is equal to the impulse that is applied to that object. The change in momentum is equal to the impulse that is applied to that object. So if we take a look at this equation, the right-hand side has mass times delta V. Those are the parts that make up momentum. So the right-hand side of this equation is equal to the change in momentum. And that means the left-hand side we're going to call the what? If this is the change in momentum, this would have to be the impulse. Okay, so let's talk about impulse. Impulse causes a change in an object's momentum. Impulse is caused, or impulse is a result of a net force being applied for a certain amount of time. So like we said, not only are we concerned with how big of a force we apply, but also for how long we apply that force. And we summarize those ideas with this equation. Impulse is equal to net force multiplied by the time. So to analyze that motion, how hard do we push? How long do we push? we'll go here. Okay. This equation, right, the impulse momentum equation, it's almost like it's cause and effect, right? This is the cause, this is the effect, right? This is what causes that object's motion to change. This is how much does the motion change, okay? So you can think of it that way. Impulse is the cause, change in momentum is the effect. Does that make sense? Okay. All right. If you take a look at the back side of the page, there's a bunch of pictures that we use to illustrate these concepts. So let's take a look at a couple of them. I changed my mind, and I'm not going to tell you about the first picture first. I'm actually going to tell you about the third picture first. And that picture relates to this guy swinging his golf club. Except I don't have a golf club to swing in this room, so I'm going to do this. Okay? What? So people at home, people watching the recording don't get to see this, but, so I got the yellow ball, okay? And I'm going to throw it in the air and I'm going to do this first. Okay, ready? Here we go. Pretty awesome, all right? So here's throw number 2. Okay? Obvious difference between throw 1 and throw 2.
Bigger.
What's bigger?
Displacement.
The displacement, yes, it went higher because I threw it what? I threw it, I threw it faster, right? Because if I throw it faster, what does gravity have to do on the way up? Slow it down, slow it down, slow it down. If I don't throw it very fast, it doesn't take gravity very long to slow it down. But if I throw it faster, it takes gravity a lot more time. Did I change this ball's momentum? Sorry, we're supposed to see that part. So, all right, but if you watch my hand when I do this, right? Here's my hand the first throw, right? Here's my hand the second throw. What's different about my hand first throw versus second throw?
For the second throw, it goes with the ball.
It goes with the ball a lot longer, right? Kitty, what part of this equation does me keeping my hand with the ball longer affect?
Impulse.
Yes, which part of the impulse?
Time.
The time. If I apply a force to this ball, I'm going to cause it to change. If I apply the force for a longer time, how much does it change? It changes more, and therefore it goes a lot higher. Anytime you do something where you make contact with something else, you swing a golf club, you swing a tennis racket, you swing a baseball bat, you throw something, you kick something, you hit something. An important idea of that is how much do you follow through? Because following through changes what part of that equation?
The net force.
No. It changes the time. Okay? If I make the time bigger over here, what has to happen over here? It's got to get bigger too, because that's an equation, right? In the case of somebody hitting a golf ball, let's say this is like a drive and we want to hit it really far. We want to make the change in velocity as big as we can. If you want to make the change in velocity as big as you can, you have to make the impulse as big as you can. So you swing hard, that applies a large force, but by following through, we are also increasing the time. And by increasing the time, you're increasing the impulse. Oh. And that increases the change in velocity. Now, do we always always want to make the change in velocity as big as possible?
No.
When you're golfing, is the objective to hit the ball as hard as possible every single time? No, right? Think about when people do putts, right? How hard do you want to hit the ball when you putt? Kind of depends on how far away from the hole you are, right? But you usually don't want to hit it as hard as this, right? So, do you swing as hard? First, you don't swing as hard. That decreases the force. But also, too, when you putt, you only follow through like this much, right? Because that decreases the amount of time that your club is in contact with the ball. If we apply it to a different sport, okay? If we apply it to, let's say, baseball or softball, okay? When you swing the bat, if you're trying to hit a home run, right? You try and swing that ball all the way through, right? Swing the bat all the way through. But if you're trying to bunt, right? You don't swing the bat at the ball, right? Because you don't want the velocity to be that big. So you try to decrease these things over here. Right? Does that make sense? You okay with that part? Okay. Next part. I'm going to flip it around on you now. The next part deals with these two eggs. Let me grab the picture of these two eggs. Let's put it here. Okay, so we got these two eggs. We learned earlier this week that if we drop these eggs at the same time, what's going to happen to them? Well, what are they going to start to do? They're going to increase in speed. They're going to accelerate. Becca, how much are they going to increase in speed? In relation to each other. The same amount, right? Gravity accelerates all objects exactly the same. So if we drop them from the same height, by the time they get here, what will we know about the speed of those two eggs? Same speed. Okay? Now, from that point forward, what's going to happen to both of those eggs? What's going to happen to them? They're going to land, and eventually they're going to do what? They're going to stop. Okay? Both of these eggs are going to stop eventually. So, if we take a look at this equation, right? There's our impulse momentum equation. In the case of both eggs, what can you tell me about the right-hand side of this equation? It's going to be the same for both eggs, because eventually they're going to stop. So, now let's go over here. If we take a look at the pillow, so as soon as the egg hits the pillow, it starts applying a force to that egg. But what happens to the pillow as the egg falls into it? It pushes down, right? The whole time that pillow is squishing down, what is it doing to the egg? It's pushing up on the egg, which means, Becca, it's doing what to the egg's speed? Slowing it down. So that pillow slows down the egg as it squishes into the pillow. But how does the plate stop the egg? Right? How long does this take versus this? Okay? The pillow takes more time. If this side of the equation has to stay the same, if my pen stops drifting around on the page, if we take more time, how much force do we need? Less force. Because we know that in the end, we have to stop the egg. Right? If time is short, right, what's going to happen to the force?
Go up.
If I only have a short time to stop the egg, how much force do I have to apply? More force. This applies in the case when the change in momentum is the same. A lot of times that's when things are stopping, right? So, we take a look at this, right? We're still going to use the impulse momentum equation to explain this. In both cases, we know that the delta V for that egg has to be the same. Why? Because eventually both of those eggs are going to stop. When the change in velocity is the same for both objects, force and time have an inverse relationship. Meaning, if the pillow is going to take longer to stop the egg, it doesn't have to apply as much force. If we go back to one of our baseball examples, right? So the catcher behind home plate, he has to stop the ball every time it gets thrown to him. Does he have to use a big catcher's mitt? Could he use his bare hand? Yeah, he could, right? But the catcher's mitt has padding. What does that padding do to the time it takes him to stop the ball? Increases the time, which does what to the amount of force? Decreases the amount of force, which doesn't hurt his hand as much. Right? Does that make sense? You okay with those ideas? The two other pictures on that page are examples of what we just talked about. Okay? Tonight, see if you can apply the concepts that we talked about to those two pictures. Okay? To wrap it up for today, you guys have been pretty good. We'll watch one more thing and we'll wrap it up. I have another video for you. Oh, sorry. Relate it back to the video. Why did we start watching today's? Why did we start today's class by watching the water balloon videos, Katie?
Because they have to give a little when the water balloon comes back to
In
them.
every single case, Katie, when somebody throws the water balloon, what is that water balloon eventually going to do?
Stop.
Stop, right? So if we take a look at the granny who was doing the water balloon toss, right? Okay. One of the times it like hit her hands and then like hit her in the belly and then like hit her in the knees and it fell on the ground. But did it break?
No.
No, because how long did it take her to stop the water balloon?
Quite a long time.
A longer time, right? But when it hit her right in the chest bone, right? What happened?
Broke.
It breaks, right? Because the amount of time it takes for the balloon to stop in that case is a lot shorter, right? When you have to throw the water balloon a long way, what do you have to do? With your arm,
Increase the force.
you have to increase the force, but also
Follow through.
follow through, increase the time. If I only have, on the first throw, I only move my arm this far, because I don't have to change its velocity very much. But if I have to throw it a lot farther, now I have to apply that force for a greater amount of time. Okay? And that leads to the subject of our next video. So, before I start this video, it's on recording, okay? This video was put together by a church group, okay? I am not condoning or trying to make you go to this church, okay? They're not really, though they kind of are trying to get it, but it's not really like, you know, it's not really like propaganda, okay? But, so I'm not like, you know, vouching for this church or anything like that, okay? It's just kind of a funny video, okay? And so, well, first let me unmute this so we can hear it, because the sound on this one is actually kind of important, so. All right.
annual picnic, Justin Hooper and Sharon Cumberland decided to participate in the water balloon toss. They were good. Very good. 853,000 successful tosses later, and they're still going. We have caught up with Justin here at Terrace Hill, where yet again he has taken a large step backwards as preparing for his next throw. Justin, what started all this?
Well, my family always goes to the 4th of July picnic for food, fellowship, and games, primarily for food. And we always fill out the tab on the side of the bulletin to give the food team the numbers they need. It would be a tragedy if they did not have enough food.
How right you are, Justin. How right you are. We will now send you over to our female correspondent, Wendy Storm.
Thank you, Rusty. I'm here at the end of the pier in Port St. Louis with the receiving end of this amazing team and her overly supportive husband. So Sharon, what are you thinking?
Has he thrown it yet?
I don't see it.
How about now? Has he thrown it?
I don't see it yet.
Well, we'll check. Is it coming?
Have you thrown it? No, he hasn't thrown it.
Come on.
Very intense down here, as you can see. All right, Rusty, tossing it back to you.
Caught that one, Wendy. Well, it is time for the throw. And the crowd is ready.
Justin!
A hush comes over the crowd. He's preparing his throw. He is taking his stance. Pull back his arm. Go, go, go.
He's running all the way there. That's good. He's gonna like float.
The eagle has left the nest. I repeat, the eagle has left the nest.
So there you go. So like I said, I'm not trying to advertise for the church or anything like that. Right? It's not my church. I have no idea where this church actually is.
I think we should go.
But
Go to their picnic.
there is a 4th of July
Probably like
picnic
Utah.
with food, fellowship, and games. But
I
make
don't
sure
know.
you let the food team know you're coming so they have enough food.
That was so
So it would be a shame. Yes, it would. All right, so tomorrow we will lab it up, dealing with impulse and momentum, and take a look at these real numbers and see how they compare to one another.
I like how his name was Rusty Fail.